So the next thing we're going to talk about with microphones that we didn't just cover last time. So remember we talked about, well, we talked about phase, right? So you want to get that stereo illusion that the brain likes so well. You need to have two recording channels for stereo to work, which means you can't do stereo with a single microphone, which is what I learned, as I said last week, when I discovered that Zoom collapses all the audio down to a single channel. So all the phase examples in the lesson on the recorded videos, you're not going to notice because there's only one channel. You need two channels of audio. To get a natural sound in two channels of audio, what is going on out there? To get a natural sound in two channels of audio, you have to use different techniques. And there's a dozen techniques to get stereo recording sound in a room. But the simplest one, if you want a simple stereo effect, if you want to have a bit of room tone, a bit of that head expanding spacing so it's more natural, is something called the XY technique. Right? And the XY technique is using two microphones pointing in this XY pattern. I don't know why they call it XY pattern. In fact, we'll get to that in a second. But you put the two microphones at 90 degrees, anywhere from 90 to 110 degrees, and splay them on a graph, on an angle, sorry, in other words, you don't point this microphone directly at the sound source, you point it at an angle of 45 degrees. This whole angle is 90, it's 45 and 45, right? You'll get a perfect stereo image with two microphones. So then we talked about phase. So let's just move on. We talked about phase. So is it a standard? No, not everybody even agrees on this. But if you guys want to just practice with this, two separate microphones, there's actually XY stands that you can buy that will clamp the microphones in that position, but you can gaffer tape them together. There's all kinds of ways you can be creative. You don't have to hold them. As long as you don't cover the front where the pickup is, you can put, attach the microphones in any way you like to get this technique. Zoom recorders, if you guys have used a Zoom recorder with a built-in microphone, you've probably seen the XY microphones on top, right? It's just a really cheap and nasty way to get a stereo signal. Here are the techniques. So the basic idea is you want to have an angle from the microphone to the sound source. And as you can see here, there's at least 6 different techniques for that. I'm just going to have to fix my window here for a second. Okay. Someone's prospecting outside my window. Okay, so where was I? Right. So there's a dozen different ways, right? But all these are valid. They may not sound the same. You may get wider, what's called separation. In other words, it may appear that your ears are further apart. When you talk about stereo separation, really what you're doing is you're kind of artificially spacing your ears apart. Your ears are naturally your head width apart, but using phase techniques and XY microphone techniques and all kinds of other techniques, you can widen or narrow that. You can have voices come out of the middle of your head. If you close your eyes, you can have voices coming far in the distance. Again, refer back to that virtual barbershop for this kind of thing, right? To hear what that sounds like if you're not clear what I'm saying. The sound will move around the room, but it'll also go wide and what's called wide and tight. So these XY techniques will give you, and any one of these is valid, right? The mid-side one is kind of weird where it uses a single microphone with different pickup patterns. I've never had any success with this. You need specialized kind of mics for this that will do that. You need to have a cardioid and bidirectional. Most people typically have the same mic. So here you've got the first 3 techniques. I'm sorry, the first 4 techniques shown here and the last one all use the same kind of mic. This mid-side requires one of each, a cardioid, and they're stacked up on top of each other, right? And it's, I mean, if you have it, you have it, right? But anyway, you can experiment with these yourselves. I would if I were you. If you use a single microphone on a shoot, for example, if you want to record room tone on a single microphone, that room would be in the center of your head, right? Okay, so that's now 10:17. You've arrived late. I'm just going to make a note of that. And as I said before, next term we're going to start marking for attendance, so keep that in mind. Back to my point. So there's the XY technique in a nutshell. Yeah, and we've talked about the 3-to-1 rule. So let's just end that for a second. We'll stop We'll pause the recording, stop the share, pause the recording. One more diagram of the 3-to-1 rule. Here it is. I forgot I had it, of just an individual, right? So here is the rule basically expressed with one subject being shown, but you do this for every additional microphone. So for every 1 meter, 1 foot, 1 unit, whatever that might be, 3 times for separation. All right. Oh, sorry about that. Okay, phantom power. You guys have probably used phantom power already. You're certainly using phantom power in a weird way. Well, it's not phantom power, no. Phantom power is when you deliver external power to a microphone. And as we know from condenser microphones, they require a charge voltage, right? And that charge voltage is to allow you to have extra electrons available to be converted into audio when the 2 plates in the condenser mic move together. So if you've seen the condenser mic video, or pardon me, not video, if you've seen the condenser mic slideshow that I put together, it's very simple, a couple of slides. You have, and I'll just stop share because I like to use my hands here. And in class, I'd be doing this. You've got 2 metal plates inside a condenser microphone. One is rigid, one moves. And the one that moves with the air, right, is charged with electrons. And when the one that moves with the air gets close to the one that's not moving, the electrons jump the gap. And that jumping of electrons is the audio that you record. The beauty of the condenser microphone is that that moving element can be super tiny, like tiny, tiny pinhead small, right? Because all it has to do really is move close enough to transfer electricity to another plate. Whereas a dynamic microphone has to have a big diaphragm because it has to actually push a coil of wire, the magnet or the coil. It has to physically push this coil of physical material. So it's got to be much larger. It needs, and so it's, you know, it's brilliant and it requires no power. And dynamic mics are really useful, but condenser mics are very sensitive. Now the downside is they're very sensitive. So you would never use a condenser mic on a kick drum or a bass guitar or someone who screams, because they're going to overload the microphone. They're going to push the 2 plates together and you're going to have nothing but distortion, right? So back to phantom power. Let's just go back to this again and share. So phantom power, it supplies that voltage for those plates. There's a number of different voltages. There's P48, I think there's P24, there used to be P9. The P is for phantom. Whenever you see P on a mixer or a microphone, that P is the next number after that is the amount of voltage you require. It's always DC voltage because the electrons aren't moving until the plates touch. So you don't want AC power, because if there was AC power on the microphone, the electrons on that first plate would keep moving back and forth with the alternating current. You want DC current, right? You want the charge to build up, and then when the plates touch, bang, right? So phantom power is usually supplied by a battery inside the microphone. So again, stop share. It's always handy to have props. I just happen to have a prop because, hey, look, hey presto, I'm wearing a microphone today that's a condenser microphone. And I've done a terrible job of dressing my microphone on myself, so excuse me. But you've all done this, right? You've all seen inside the capsule, right? Oh, faced the wrong way. There's your battery. That is supplying the charging voltage to the head of the microphone, right? And that charging voltage is what's going to be turned into audio when the air starts moving that plate, okay? So that's phantom power. That's internal phantom power. External phantom power comes from usually mixers or batteries. The danger with phantom power that's external is it can drain batteries very quickly. All right. Phantom power was never conceived way back in the day to be a battery source. Most phantom power sources were plug into the wall. So you had an endless supply of DC voltage that you could just, the converter would turn the AC into DC and supply it to the microphones. Nowadays, we use a lot of batteries. And so phantom power can be a real power drain. So, you know, beware of that. So let's go back to sharing. Start share. Start share. Okay. When you use phantom power externally, don't leave the battery in the microphone. Some companies like Sennheiser and Neumann will have what's called a dummy, which is just a metal piece that replaces the battery. You put that inside the microphone instead of the battery. Some will operate without the battery in it. You'll find out in a matter of moments if there's no sound, it needs a dummy replacement. But never leave the battery in if you're running external phantom power, right? Okay, so that's phantom power talked about. It's very straightforward. It's a charging voltage for condenser mics. Dynamic mics don't need them. If it's not a condenser microphone, it doesn't need phantom power. Now let's talk about wireless microphones. There was a brief discussion about this last week, and I said I would get to it this week, and I will. Strictly speaking, a wireless microphone is not a microphone. Strictly speaking, a wireless microphone is a radio with a microphone attached to it. Okay, so we use the term wireless microphone in shorthand, and it's pretty obvious when you think about it for a second. But again, in this industry, there's lots of jargon, and people can't be faulted for assuming that when they hear the term wireless microphone right off the bat, that there's a microphone with no cables coming out of it, and therefore it's a wireless microphone, right? No, a wireless microphone means in our industry a radio transmitter with a microphone attached. The microphone can be any microphone. Right? Any kind of microphone can be made wireless. I don't know if I have, yeah, so I do. I have an illustration here showing an inexpensive wireless set. You can plug in a lavalier to a wireless. You can have a hand mic. You can have a fish pole. There's all kinds of ways you can use wireless microphones, right? They're very handy. There's a number of different frequencies. Those frequencies are changing over the next few years because the government keeps selling the prime frequencies off to internet providers. You know, 5G was only possible because of a lot of frequencies were sold to internet providers to now replace audio signals like wireless radio with 5G. So what I'm saying is be careful what you buy right now. A lot of microphones will become illegal in the spring. I think it's 2021, if they're not illegal now. With this whole COVID year, I lost track. But I think it was this year or next year when a whole bunch of frequencies are no longer able to be used for wireless because they're going to be used for 5G. The danger, of course, is that all those transmitters won't go away if you're a 5G person, and you might have some issues with interference. Anyway, some wireless microphones, and I've used one years ago, it was kind of an old school clunky thing, used a laser instead of a radio frequency. So it was a wireless microphone. The transmitter was the size of, maybe a DSLR. It was pretty big for a transmitter, but it was a laser transmitter. And so you had to point it at a dish. And we used it in a sporting event, and we pointed at a dish across the stadium. The beauty of it is that no one else can listen in. The danger with wireless microphones is anyone with a receiver can listen into your wireless microphone, right? With a laser, it was point to point. The problem with lasers, they're very impractical. The day we used it, actually, it was at Empire Stadium. No, it was at, where was it? God, it was so long ago. I say Empire Stadium, that dates it. But nonetheless, it was a football game, and it started to rain, and then the laser broke up because the rain got in the way. But there are different systems of wireless microphones. The vast, vast majority are radios. As such, though, and so this is the important part about radios, and you'll notice this if you've already used the wireless intercoms, any radio is affected by the environment. So fluorescent lighting uses, transformers. Some LED lights, I have them in my house. They're very cheap LEDs that I bought at the local home improvement store. And these lights give off radio frequency because, and I'll just stop share for a second because again, the hands, a lot of LED light fixtures use what's called a diode bridge or a cheap, well, let's not get too technical. They use a very inexpensive way to make the LED function. And that inexpensive way broadcasts tons of radio frequency as a byproduct. The manufacturer of the light bulb doesn't care. They've achieved their goal. They made the LED light up. But everyone else in the room that's dealing with radios suddenly has all this interference equivalent to having a microwave oven turned on, right? So you can end up with interference from simple light bulbs. And as I say, I have a couple in my house. I know where they are. I don't use wireless microphones in my house, but I do use some wireless items like Bluetooth earpieces, for example, that are wireless, and they will act up when I walk by these light fixtures. It's very frustrating. And that's because it's cheap construction. If we go back in history 40, 50 years or more, there were regulations about what kind of radio frequency your device could emit. Now those regulations, most of them have not been updated in 50, 60 years. So as a result, these modern devices that emit all kinds of spurious RF information aren't covered and therefore aren't restricted in being the way they are. So of course, manufacturers always take shortcuts, right? Because they want to get good margins and, or they don't care. You get people making things in countries where jurisdictions don't care, and you just get the market flooded with this cheap stuff. And people like us doing audio suffer because now you've got all this, you're basically in a soup of all this RF, all right? So where was I going with that? I don't remember. But let's go back and share. That'll help me stay on track. Oh yes, wireless microphones, right. So electrical interference, fluorescent lights, electric motors, internal combustion engines are notorious. So if you're shooting a scene inside a car with a wireless microphone, you could potentially get a lot of interference from the DC powered engine, right? The car engine has a direct current battery that charges the spark plugs that cause the engine to fire. All those things give off, every one of those sparks gives off a blast of RF when they go off, right? Other radio transmitters, if you're near a strong radio source, if you're at the airport, a good example, a lot of television news people, you can ask people like Sia who do news, know that as you get closer to the airport with their giant radar domes for navigation, RF can be interfered with very badly, right? So keep that in mind. It's not a reason not to use it. It's just something to be aware of. It helps you troubleshoot. You know, you start thinking, well, my radio worked fine in the building. It's not working fine now. Is it the battery? No, it's not the battery. Is it the microphone cable that you wiggle a cable to make sure that's not crackling? It's not that. Well, where am I? Oh, I'm in a generator room. I'm in a, we're at a bus station, trolley bus area. All those things are going to get off RF, and that'll help you troubleshoot those faults, right? Yeah, and there's a bunch of various variables. That's all this is really trying to point out. There's so many variables. We don't have time to go into all the details with RF, but understand that when you work with wireless microphones, you open yourself up to a whole world of hurt, potentially speaking. The cheaper the system, the less agile it is. And so you'll notice, for example, that this Sony system has 2 antennas. And what that means is the receiver has 2 different receivers built in. If one isn't getting the microphone, it automatically kicks over to the other one, right? So that therefore it's much more, we use the term robust. It's much more solid when it comes to having a breakdown. You're unlikely to have a breakdown if you've got multiple receivers. These are sometimes called diversity receivers because they have diverse numbers of reception. Some have up to 4 antennas. You'll see this if you're familiar with IT, you'll see this very principle put into effect on your house Wi-Fi. A lot of Wi-Fi routers nowadays have at least 2 antennas, some have 4 or more. This is what they're trying to achieve. They understand that your wireless source, your laptop, whatever, your phone, is moving around the house. And as it moves around the house, different antennas are going to have stronger and weaker abilities. And so you're never going to lose signal by having multiple stuff, right? If you get cheaper stuff, you don't have those same things. So tons of variables. Again, we don't have time to get into all of them, but just understand that RF isn't as solid as it appears. If you depend upon it, for example, if you go on a shoot and never have a wired microphone, like a dynamic microphone with a cable, you're opening yourself up to trouble, because if the wireless system fails, you got nothing. And they can fail and they will fail. They just are. The more technology you ever put on any situation, editing, whatever, you name it, the more technology you apply to the problem, the more likely there is to be something going to go wrong with it. Okay, mic specs. Ooh, what time we got? Oh yeah, we're good. So I'm going to give you a quick oversight of microphone specifications. This is to help you guys choose microphones. All right. We've talked about some of these specs already. This spec sheet, sorry, it's so tiny, but this is a classic SM58 vocal dynamic microphone, right? What I'm going to do is I'm just going to go through some of the specifications to help you understand how to choose a microphone. Again, a lot of you are probably at the phase in your phase. I used a pun there almost. A lot of you are at the point in your development where mic choice is down to, is there a microphone? Yes, that's the one I choose. We call that the love the one you're with syndrome, which means whatever microphone you have is the one you use. And that's fair. You'll often be shoved out onto a situation where you only have one choice. You don't get to choose at all. So then what it comes down to is, if you've got the microphone you have, how best can you use it? But in order to help you choose a microphone, if you're looking at buying them or whatever, it's important to understand some of the specs. So let's go through some of the specs here on the spec sheet very quickly. So the first thing you know, it's dynamic, right? Dynamic means it's going to be all the issues of a dynamic microphone. It's going to be good for voice ranges. It's going to be taking a bit more air power to move it, so it's not as efficient as a condenser microphone, which means it won't be as loud. which is good if someone's a screamer, like I said before, you know, or you've got a loud instrument you're going to mic, like an electric guitar amplifier. You wouldn't put a condenser microphone in front of a guitar amplifier or a piano necessarily. Well, you might for a piano, never mind. But for electrified instruments, you definitely want to use something dynamic. The frequency response is at what frequencies do the microphones respond to? This is irregardless of the polar pattern, we'll talk about in a second, because we talked before about how the polar pattern changes shape depending on frequency. But if you add all those patterns together, the microphone will pick up sound as low as 50 cycles and as high as 15,000. So not good for ultra high audio. If you want, for example, to record cymbals. I'm going to go back to my musical instruments because, sorry, that's kind of where I started out and where a lot of my examples come from. Cymbals have a very high octave sizzle sound, higher than 15,000 hertz. So you wouldn't use an SM58 on a cymbal. You'd use a microphone that has a higher frequency response. So you'd want 50 to say 20,000 hertz, right? Or 22,000 hertz to capture that snap and sizzle of a cymbal. But for human voices, which are somewhere between, you know, 500 and 5,000 hertz, this is perfectly suitable. And for most everything else as well, right? Most people's hearing after the age of 30 starts to tail off at 15,000 cycles. You know, when you're in between the ages of 0 and 27, you're in that ideal 20 to 20,000. You're probably actually 20 to 24,000 cycles. As you age out, it starts to taper off. So that's frequency response. That's what the microphone does. The polar pattern, cardioid, we talked about that, the various shapes of pickup patterns. The sensitivity, I'm not going to go too far into this stat other than to say that the higher the number, the better. There's no point talking about this number today because we haven't talked about decibels, but we'll come back and talk about this at a future point. I promise. We'll talk about sensitivity. But what you basically want to know is how much voltage will this create with a certain level of input air pressure. And we haven't talked about any about that today, so it's too soon to discuss this at the moment. Impedance used to be an issue, not so much anymore. The thing to remember with impedance is always match your impedance. So if your microphone is rated 150 ohms, which is low impedance, then make sure you plug it into a low impedance input on a mixer or a camera. The beauty of that is that most mixers and cameras use the shorthand of mic and line for this. So you'll know that a mic goes into a mic input, right? Again, there's a lot more to impedance than this, and we'll talk about that at a future point. Polarity is basic. This is an old school stat that we don't really need anymore. It's saying that pin 2 is positive, right? It used to be pin 3 back in the day, but now it's all pretty much pin 2. There's still some European stuff that's, I think, from the 70s and 80s that's around that's pin 3. That's all this is telling you, right? Don't worry about polarity. And then the rest of it's just the physical stats, okay? So that's one series of specs. The next thing is, and I'm gonna see if I can, oh, there we go. Zoom in on this. So here's your polar pattern. Remember, it said cardioid in the text, right up here, but here's where you can actually see that cardioid shape, just to confirm it. You can also see the dotted lines for the different frequency response. You'll notice at 125 hertz, the solid line at the back, it's almost omnidirectional, right? But at a very, very low frequencies. Anything above 500, which is getting into the range of most audio, is immediately cardioid, and for that point forward. The frequency response, so here's a graph that shows you how flat the microphone is. Now this microphone has what's called a peak from 2,000 to 7,000 cycles. And what that means is it's more responsive here. So if this microphone was going to be used for accuracy, it would not be suitable. For accuracy, you want the frequency response to be 0 all the way along, what's called a flat response. You want the microphone to not add any energy or take any energy away. You'll notice, for example, above 10,000 cycles, which is this last section here, the line drops down. So that means the microphone's less sensitive and recording less and less energy as we go higher in frequency. It's not flat. It's also not flat from 50 to 100. Right? It takes a while before it gets to the 0 sensitivity. It's actually taking away. In other words, any sound that this records at 50 cycles is going to be down probably about 2 or 3 times normal sound level, right? So this microphone has what's called an emphasis curve, which are these little bumps here. And where is this little bump? It's right around 4,000 to 5,000. Why is that nice? Because that's a good place to have an emphasis for human speaking and singing. So when you see this emphasis curve here in the middle, you think, well, this is a great vocal microphone, right? If there was an emphasis curve down at the bottom, excuse me, in the bottom frequencies, you think, oh, this would be a great microphone for a bass guitar amplifier or a drum kit or, you know, something like that, all right? So that's the frequency response. And that's basically all the specs that we need to get into today. That was just kind of a quick overview. That should give you enough information to choose a microphone based on some of that. All right, so I'm going to stop the share. We'll stop the recording. Dang it. I'll do that again for the recording. Okay, take two. No, that's actually good. So it's good to recap it anyway. So back it up. Remember the important point. Low impedance is better than high impedance, right? Professional quality microphones, professional grade microphones are low impedance. 300 ohm, 150 ohm, anything low. Anything in the thousands of ohms, 5,000, 10,000 is high impedance, low quality, right? Usually. Not suitable for professional use, okay? So what is impedance? Impedance, although measured in ohms, is in fact the combined effect of everything in the circuit. So resistance is the quality of a single thing. A wire has a resistance to electricity proceeding through it. A circuit will have resistance for sure, but if you combine all the other effects besides resistance, like inductance from transformers, the capacitance of capacitors in the circuit or condenser microphones, all these things will work together with resistance to delay the signal, to impede the signal, right? Hence the term impedance. So we use the letter Z as shorthand for impedance. So you'll see high Z or low Z, or if you know American pronunciation, high Z or low Z. But the impedance is measured in ohms. Well, it's actually, yeah, it's measured in ohms. They use the ohm symbol, but it's not strictly resistance. So if you see an impedance number, it's not just the resistance. Now, having said all those things, you don't really need to know that. You just have to understand that it's different than resistance. Resistance, I'll just repeat for the sake of clarity. Resistance is the quality of a single device, such as a wire, a light bulb, a speaker. A single thing has resistance. The combined effect of the resistance, capacitance, and all the other forces that slow down electron travel through a device is called the impedance, okay? So to use an example, home theater speakers would have 8 ohms of resistance because the speaker is a single device. The impedance of the amplifier driving those speakers would be another number altogether, right? And that's really all there is. All microphones have a specific impedance. Here's the rough idea for impedance ranges. Low impedance, 600 ohm or less, professional. Medium impedance, 600 ohm to 10,000 ohms, and high impedance, you know, consumer grade stuff, 10,000 or higher. Some microphones have switchable impedance settings. Not so much anymore because, again, most of this industry has standardized on low impedance. So unless you go buy something weird for microphones, and again, impedance is only an issue for you for microphones, I wouldn't worry about this too much. It's just a thing to know. And the answer is usually low when it comes to which impedance do you choose? Usually low impedance. Because remember, low impedance means more current's going to pass through, right? It's better. Lower resistance is better for current flow. And so low impedance is better for the same thing, all right? For the same reasons. And this, I don't need to go into this. I'm going to skip. I might take these slides. This kind of breaks down impedance on, well, okay, you know what? Maybe I should explain why low is good. It's because high impedance microphones, the frequencies start to roll off. In other words, they start to disappear over distance. The good thing about a low impedance microphone is that you can have 20, 30, 40 meters of cable and not lose any frequency response, right? So that's why you'd want low impedance. That high impedance takes electrons out of the game, and those electrons usually disappear from the high frequencies signal first, all right? And I'm going to take these slides out, I think. Okay, frequency response. I talked a bit about it. I'll just go into a bit more detail. The way the microphone, this is a frequency response when we talk about microphones. It's the way the microphone responds to different frequencies. Okay, it's a characteristic of all microphones. Some frequencies are exaggerated, some are reduced. You saw that before in the spec sheet. That Shure microphone had a boost in the 4,000, 7,000 range, right? So here's that same chart again, just showing you this rise at 5K in the human vocal area. So this is actually good because you want to emphasize this range of human speech. I mean, humans make a bunch of sounds in these whole areas, but our speech is generally in this area. So a microphone that emphasizes that is going to just be more clear. It's going to have a better sound. Could be a little bit warmer if there's a bit of a tail down here that, you know, emphasizes the bass. So definitely a good thing to have, unless, now I say that, that's a quality statement. That's not a scientific statement, because if you want an accurate representation, you want this line to be flat, right? This line is not flat, therefore it's going to emphasize this frequency. It's going to sound different than natural. It's going to sound unnatural, but it's a pleasing unnatural, okay? So frequency response also affects the polar pattern. We talked about this briefly before. You can see that 125 hertz on this same microphone that we just looked at, it's almost omnidirectional. The frequency response is almost a circle, not quite. It's a bit flattened, but it definitely becomes cardioid with that notch at the back. So if this is the front of the microphone, the 0, by the way, is the microphone pointing down. If this notch at the back means you're not going to pick up any sound back here in those frequencies. The bad news about this microphone with this notch, with this almost circular low frequency response, is that it will pick up things like touching, handling, bass sounds, thumps, booms, bangs from behind, right? So this microphone is, someone would say this microphone is probably susceptible to handling noises and therefore should be in some sort of mic clip, not necessarily in your own hand, all right? Because your hand makes a rumble sound when you touch and move your fingers on the microphone, and this might pick it up more. And then as you see the frequencies get higher and higher, the response curve changes even further. It's still generally cardioid, but there's a bit of a peak again at 2000. You can see there's a bit of a peak at the back, right? I wouldn't worry too much about these things. You're only after the general cardioid shape, but understand that frequency response will be different for the polar pattern. You might notice a microphone when it's a bit what's called off axis, when you're not talking directly into it, the high frequencies disappear or it gets really bassy. That's because of this. So the flat response means the microphone is equally good in all frequencies. It's theoretically ideal. It's practically impossible because of just the manufacturing processes in objects. It's very difficult to make a microphone with a flat response. It is done, but they're very expensive. A flat response isn't always desirable because sometimes you want that emphasized frequency, right? The main thing, as this slide says, is avoid response patterns that emphasize the wrong frequency. So don't use a microphone with a vocal emphasis on a drum, on a bass drum. Don't use a microphone with a bass emphasis on a voice. It's going to make the person sound muddy and you know, just, they're not going to sound natural. Okay. Oh. What else? Oh yeah. So some miscellany. Let's talk about the XLR connector. Pin 2, remember I said before that microphone said that pin 2 is positive. So pin 2 is always hot. If you're ever doing any repairs on a microphone or a microphone cable, pin 2 is always the positive signal. Pin 1 is the ground and pin 3 is the negative, okay? So if you use this analogy with a home power plug in your wall, this is your grounding plug and these are your 2 prongs. That would be the kind of the equivalent. And in your home, there's the fatter prong and the narrower prong, right? So even the home is now becoming polarized for electricity. But audio has always been polarized. It has to be, because if you reverse pin 2 and 3, then you invert the phase, right? Now, instead of it being positive, it's negative. You've now inverted the phase of that audio signal. So you always want to make sure it's pin 2 is hot. I don't know why this is here. I don't know if you were, I think because in previous years, Ken and Dave weren't covering this, so I'm going to go over it very briefly. Windscreens, foam sock, blimp with a badger on it, sometimes called a dead cat. It's just that the fur on these things slows the air movement through this. So this big blimpy shape, if you've seen them with the covers off, is just a cage, right? And the idea of the cage is to keep wind from touching the microphone. Well, this cloth covering, the hair on the cloth slows the air down even further, keeps the microphone quiet, all right? Pop screens, we've talked about that briefly. Pop screens are to stop people from popping their peas and spitting on the microphone. It's also a way to use put a spacer in to go back to your 3-to-1 rule, right? You can position the pop screen to force a singer or a vocalist back by pushing the pop screen back a little bit to get a bit of space. Shock mounts, you guys have dealt with these. Basically just a spring or a bunch of cords that again prevent that low frequency. Like in the case of this shotgun microphone, it's going to have a rear try that again. The shotgun microphone is going to have a rear lobe of sensitivity, and that means it's going to pick up sounds from behind. So if you isolate the behind with elastic bands, there won't be any sounds for it to pick up, right? Boom stand, desk stands. I think you guys have covered that in the other class. I won't put these last couple of slides, I won't put in the quiz, okay? They're there from the previous year. I think Ken and Dave said this year they were going to cover some of this, and I hope they have. So remember the final notes about this. Once you've got the right microphone based on specs and response and polar pattern, it's all about placement, where it goes to get the proper technique. The lavalier, the simplest placement, is as close to the mouth as possible in order to get the best signal. Always make sure the capsule is pointed up. I think this is the last slide. Yeah. So good technique can overcome bad gear, but not even the best gear can overcome bad technique. All right. So you can have fabulous microphones. If you don't use them properly, it's not going to work. I'm just going to show you. We'll stop the share. I'll show you again. So just take my careful because it's probably going to be noisy. There we go. Take my lav off. You can see the lavalier. The capsule's here. Always have it pointing at the sound hole, right? I always use the sound hole example for the mouth. It's like a guitar. This is where the sound's coming from. The capsule has to point at that place. All right. So that's part one. Done. Okay. So just keeping in mind to remember that transducers are another name for speakers and microphones. It's the category of device. It's turning one form of energy, in this case acoustic energy, into electrical energy, or reversing it, right? A speaker is turning electrical energy into acoustic energy. It's a transducer. There's a number of different kinds of transducers, but that's the basic category for both speakers and microphones. And that's what this is. This diagram is showing. That's a good opportunity for quick pause. Okay. So microphones turn sound waves into electric current through various mechanisms. And speakers, now speakers, the interesting thing about speakers is they generally use a single method. Audiophiles would argue with this, but they generally use a magnetic excitation of a physical object like a cone to turn electricity into sound. There aren't a whole bunch of different ways the way there are with microphones. There are a few others, but for the most part, it's this. So that even includes earbuds and headphones. They use a magnetic field changing to move a membrane to make sound. So a speaker is a motor. Basically, if you think about what a motor is turning inside a magnet, right? This is how electric motor works. So a speaker is doing the same thing, except that instead of rotating, it's a linear motor. So if anyone's ever taken SkyTrain, and I mean not the Canada line because that's a different technology, but the SkyTrain is a linear motor, right? There's a magnet in the track, and there's a magnetic material in the train, and the magnet in the, is the magnet in the train or the track? It doesn't really matter. There's a magnet in one and a magnetic material in the other. And by moving the magnetic field along in a line, that's what moves the SkyTrain forward. Well, the speaker's the same thing. By energizing this magnetic coil in a linear fashion, this piston will move in and out. And this piston on a speaker, here we go. This piston is attached to this paper cone. It looks an awful lot like a toilet paper roll in some speakers. And this magnet is, it's hard to see. Let me just see if I can, there we go. The magnet's here. This represents those wires. So if I just go back, these wires here that are going, in a coil are these wires here, just shown kind of cut away, right? So this magnet moves back and forth on this cone, on this, cylinder. The cylinder is glued to this cone, right? And if we go back out, the cone then moves back and forth, and pushes air. That's it. So by changing the polarity north and south, remember the sound wave, the acoustic sine wave goes up and down, up and down. So up, the speaker cone goes out, down, the speaker cone goes in, and there you have it. That's the entire technology behind speakers and headphones. All right. Oh yeah, speaker video.
Interaction between electric current, a copper coil, and a simple plastic membrane. The current and coil cause the membrane to vibrate. The membrane pushes and pulls the surrounding air. Essentially, it pounds waves into the air, sound waves. By controlling the electric current that moves this small plastic lining, the speaker can make any sound imaginable. Let's look at how it works.
So here's where it kind of falls apart for me. We spend a lot of time taking the speaker apart. So I'm going to get to...
And one for highs. Both have the exact same parts and work the exact same way.
Okay, so that I shouldn't have skipped that because that's important.
In the enclosure are two speakers, one for low sounds and one for highs. Both have the exact same parts and work the exact same way.
So that's an important thing to remember, that a woofer and a tweeter and a speaker work in the exact same fashion. They're just tuned to different frequencies.
Permanent magnet, a diaphragm, just a plastic membrane. Stuck to the membrane, a copper coil. The coil is inserted into the magnet. When the current circulates through the copper coil, it creates an electromagnetic force that pushes on the coil. By changing the direction of the electric current in the coil, we change the direction of that force. So, the coil is pushed one way when the electric current circulates in one direction, and the opposite way when the current changes direction. Since the coil is attached to the diaphragm, where one goes, the other goes too. This interaction is the key to understanding how a speaker works. All of this happens in a fraction of a second, because the current changes direction very quickly, up to 26,000 back and forth times a second. How often the direction of the current changes depends on the sounds the speaker is required to make. Low notes will get the current to move back and forth about 40 times in 1 second. That means the diaphragm will vibrate 40 times in 1 second. The faster the current changes direction, the faster the diaphragm vibrates and the higher the sound coming out of the speaker.
So one of the things that goes on inside a speaker, and then we'll show this here, there's this device down here called a crossover. And what the crossover does, it filters out so that the big speaker doesn't get the high frequency and the little speaker doesn't get the low frequency. And that way you can direct the big speaker to do more work in the bottom frequencies and have the little speaker do more work in the high end, right? So that's basically the nutshell of a speaker, a multiple speaker system. A single individual driver wouldn't have a crossover. The wires from the system would be hooked directly into the speaker, right? This is what headphones have. They have a single driver usually, all right? So that's the whole nutshell of speakers. There's not a lot to it. We'll stop the share. We'll pause the record. No point in recording the video, as I discovered. YouTube will take it down, so I'll just record my part and we'll tack it on. So that's basically the essence of noise canceling headphones. What are the cautions about noise canceling headphones is when you use them, they are actively changing the sound going to your ears. So when you're doing editing and post with noise canceling headphones, turn off the noise canceling feature, I implore you, because otherwise you'll get an artificial sound that has been created. The other thing to remember is that not all noise canceling headphones are good at it. As he indicated in the video, it's expensive to create. It was expensive in the 70s to create noise canceling circuitry, and it still is. So good quality noise canceling headphones are going to cost you somewhere in the range of a couple $100, at least. You could spend more than that, which is why you'll see lots of cheap noise canceling headphones, and the noise canceling itself is sort of good enough to get rid of that loud drone, like he says. They were originally designed for airplane passengers. That was the big market for them, for business passengers. But now we're using them for all kinds of things. They are really only good at eliminating a constant sound in the background. So people talking, dogs barking, other things don't work. And in fact, sometimes what will happen is the noise canceling circuitry, if it's not very sophisticated, will kick in when it hears some of these impulsive noises, make changes to the sound you're hearing, and could affect what you're listening to. So keep in mind that although noise canceling is a great thing, and it uses, remember, it uses phase cancellation. So something else to keep in mind is when you don't hear anything in noise canceling headphones, and some of you may have experienced this, that doesn't mean there's no sound coming out. It just means that you'll probably sense it as an increased pressure, depending on your sensitivity to the headphones. You put in a pair of noise canceling headphones on and you turn them on, it actually feels like the air pressure inside your head's gone up a little bit. I'm gonna ask, some of you may know what I'm talking about, some of you may not have any idea, but the fact is that the speakers are actively working to counter that sound. They're creating the anti-phase of the original sound outside, okay? So you can't get rid of the airplane noise. The microphones listen to it, and we'll use the airplane example because it's a constant droning. The microphones and the noise canceling headphones pick up the airplane noise. They feed that into your ears, mix it with the music that you're listening to or the podcast or whatever, but they invert the phase of that airplane noise, which means you have added sound coming into your headphones, okay? Just because you don't hear the airplane noise anymore, it's because another sound has been imposed on top of it, all right? That sound cancels out the first sound, so again, this might blow your head up a little bit, it sounds like you're hearing nothing. But the headphones are actually actively working. And you can test this by simply running noise canceling headphones with nothing going into them. You're not playing any music until the battery dies. Well, how would the battery die if nothing's happening? The microphone's working, the diaphragm inside the headphones are working, they're doing something, they're just inverting the sound you're hearing, okay? So my point is, as an audio person, if you're doing any kind of mixing or audio recording, please make sure you turn off your noise canceling feature. And that's all I have.